So today we have a short subject that's on BEMD. BEMD is bidirectional EMD. It generalized the EMD to two dimension. What I'm going to show you was not up to date. The up to date one has been developed, but I cannot share that with you in this class because we are filing a patent. Once the patent's done, then we'll post it on the web, then you'll be able to use. Yeah. So to generalize EMD to two dimension seems to be a logical thing to do, but there are difficulties. For example, whether we have two-dimensional Hilbert transformation or not. See, one-directional time series give you two dimension. Two-dimensional data Hilbert transformation, I don't know what you will get. So that is the part of the difficulty. Okay. 你们两位叫什么名字啊？你们是不是都是选课的？没有选课，你也没有选课，你们两个都不是选课。哦 ，OK， 那好。So generalize this to do the two dimension is very useful, but it has its difficulty. The first difficulty is how to identify extrema. Yeah. Two-dimensional extrema is, well, extrema is very easy to identify, but in two-dimensional, there are problems for saddle point. A saddle point is you can't see like in the hill. On one direction it's minimum, the other direction is maximum. So, what do you consider this? Will this be a maximum or minimum? Using extrema. You identify all extrema, you put a surface through all the maximum, put the surface all through the minimum. But when you encounter this saddle point, that becomes a problem for two dimension. Not only that, ridges and valleys are all also a problem. Ridge, a mountain ridge. A mountain ridge, of course, is maximum, obviously maximum from one side, but it's not a maximum along the ridge. Along the ridge, a certain point is higher than this particular point. So even identify extrema present a problem. The second one is less serious. It's how to find a spline surface. A spline surface going through all the extremas. It's not trivial. It's very computational expensive. Okay? The final thing is also technical. How to fix the edge. The edge problem is much more serious than the one-directional endpoint complication. So all of this made the two-dimensional EMD a much tougher problem than one-directional. Now, think, if two-dimensional present this kind of problem, how about three-dimension? Can we extend this to three-dimension? Yeah. Three-dimension is even tougher. Two-dimension, you can still visualize. Let me see whether we have a visualization. Yeah. Two-dimension, you can visualize. I can find, you close your eye, you think that you see a topography map. The topography map has maximum, minimum, maximum, minimum. So you put this big surface, cover all the maximum, put another surface, cover all the minimum, and then find the medium of that. That's an easy extension of one dimension. But if I have three dimension, what kind of surface or what kind of body can you connect? Yeah, I have a simple problem is that I have a lot of spheres. And sphere has density difference. Each sphere has density at center. the most dense part. So the maximum, local maximum is the center. And I have a box full of these little spheres, and each one has a different density. What kind of surface are you going to construct? How you connect those surfaces to make sure that you get the three-dimensional generalization of this? That's, again, not easy. So this two-dimensional spline, how can we get this two-dimensional spline? There are many methods. The first one is radial base function. Yeah. The second one is thin plate. The radial base function, I will go through that later. The thin plate is that you assume that you have a piece of cloth. Okay. You threw this piece of cloth, cover everywhere. Okay. So then this piece of cloth will be supported by this high spot. Yeah, like you spread through a tablecloth over this chair. That this tablecloth will be supported by the high spot. But then it also depends upon the flexibility of this particular cloth. With that also supported by this, most likely it will not supported by all the local extremas. So in this one, you have to be a little bit careful about the about the elastic property of these thin sheets of material you want to throw down. Then there's also Delaunay triangulation, and that is a sure thing. You connect all this to triangle. But to triangulation, when you come out, when you finish, you get a triangle piece of surface, but that's not the surface itself. Okay. Then by slice, I cut the picture by thin slice, and then I do each slice, and then I cut to other direction. So there are many different different ways you can do that, and you can also do NURBS, which is non-uniform rational B-spline. Yeah, and this, the last method, it's a very popular method used in machine design. That's computer aided. So all of this method you can use. Now each of this has certain difficulties. Like first we see the radial base function. What is the radial base function? Radial base function means that you write a function that is the radial base function is based on the position x, and this x to its neighbor. From x to its neighbor is related by a lambda times a phase function. This is the radial base function. This is the low degree a low degree polynomial. It can be any number of functions that you find. Okay, and this is the coefficient. This is the real value function, is called the base function. This base function has many different forms. You want to relate. You identify what we're doing here is you identify x. X is all the this this is some problem. This is actually x is all the collection of all the extremas. Okay, for each extrema you want to relate the extrema to the next point. How do you relate? You can use cubic function, you can use spline, you can use all kinds of other functions. So what are these functions form that you can use? You can use all kinds. You can use linear, you can use cubic, you can use thin plate, you can use Hardy method, you can use all kinds of functions related to the next numbers r. If you use linear, then you just connect each of this function to the next function, the nearest extrema, by this function of r. Okay. But from one point to the next, you connect. From this point come to the other, you also connect. So you want all this connection to be unique So what happened is that you have to write all of this up for every one of the extrema, and you set up a system of equation. You have to solve all the equations at the same time so that you don't have a conflict. Now because of that, the radial base function means that you actually will solve if you have n extremas. It means you have solved n simultaneous equations, and depends upon the radial base, depends upon the base function that you select. And this may be nonlinear, may be cubic, may be logarithmic, may be whatever. So this function is not easy to solve. Therefore, the radial base function is very, very time consuming. Yeah. And so you have all kinds of different functions that you can use. And each of these functions, then you have to solve a simultaneous equation including this function with different r's. Yeah. So the other thin plate is that if I throw a thin plate, I want this plate to comply with all these extremas. Then in that case, you have to adjust this function so that you make sure that this function is so flexible. It will touch every single extrema. You don't have any exception. Yeah. And that, again, is not an easy thing to do. The third one is Delaunay triangulation. The Delaunay triangulation simply stated is like this. For each extrema that you connect your neighboring extrema by straight lines, so you form triangle shape. So in this way, you can connect everything. But the problem is that how about this? How about this? The edge. The edge may, in this case, so they have already filled up the edge. The edge may not be extrema. Very few edges are extrema. How you solve the edge problem is another problem. And even forget about the edge. Just look at this connection. After you connect all the maximums, you form a surface. This surface is like a broken line. Each section is like a broken line. It's not smooth. So Delaunay triangulation, the next step is to how to smooth this surface. To make this surface smooth, and not only maximum smooth, also minimum smooth. So this smoothing of this surface would take a lot of computation, and also you have to interject certain subjective thinking in smoothing. So this, again, is not that easy to handle. And this triangulation, if you look at the triangulation, if you have a lot of extrema, you finally get this kind of envelope for maxima from this triangulation. Yeah. This is after many steps of smoothing, and this is not a straightforward operation again. With all this approach, so people has already applied it. So sure, it take more computation time, but computation time, it's okay. We got lots of computers, and the computer is getting more powerful. We just brute force and do it. See what we got? For example, if you get a piece of cloth like this, and this original image has texture, this little structure, which actually is in the small pattern, and they are large patterns of defects. So if you use two-dimensional EMD, you can separate this texture and the background clearly. This one has only small structure information, and this one has only large structure information. So two-dimensional EMD actually works, and it'll work. You can detect those defects, the defects in your original image. I think this one has a problem. This last structure goes with that. Here you have a slight lighter structure here. You have a lighter structure here. It all showed up. So this give you a tool to examine your, like for example, this is a fabric factory building fabric. Then you can detect the subtle change of the background pattern. And here is another image. This image is a shot of the ocean surface. Ocean surface with bottom topography, with a little bit bottom topography. This picture actually is generated by synthetic aperture radar. Synthetic aperture radar is a radar with the focal point. The resolution of an image depends upon your focal point, and no radar can carry very large antenna because it's physically impossible for you to carry huge antenna. The larger the antenna, the better resolution that you got. So synthetic aperture radar does not use one aperture, but use synthetic aperture. What it does is that it fly over the surface. It will take picture at a different angle, and then reconstruct this angle as if a big aperture can look over the whole ground from different time. So synthetic aperture radar even fly in the height of say 800 kilometers. It can get resolution to about 20 meters, 25 meters, yeah, with very small antenna. This is one of this picture that you actually see the rough surface and also a certain feature of the ocean bottom. This is one of the first things that the synthetic aperture radar surprised the people. When they flew the synthetic aperture radar over shallow ocean, they find all kinds of bottom topography, and they were surprised to find this because radar does not penetrate the ocean. Radars, the electromagnetic wave penetration of the ocean surface is only a few millimeters. Then how can you see the bottom topography? And this is a big puzzle for the research people, for the oceanographers. Not only you can see bottom topography, synthetic aperture radar can also see signature of submarines, and that is why the synthetic aperture radar was classified by U.S. Navy. U.S. Navy come out after they saw the first synthetic aperture radar from the first sea satellite, CSAT-1 in 1978. The Defense Department of the United States told NASA, stop using synthetic aperture radar. So from that time on, no more synthetic aperture radar from NASA was used in the satellite, even though synthetic aperture radar is a very, very useful thing. So as a result, NASA's remote sensing research almost stopped in looking into the sophisticated mathematical and physical processes. But U.S. Defense Department cannot stop European or Japanese or even Canada. So now all the synthetic aperture radar image are all from Europe, ERS-1, ERS-2, and Canada, RadioSat, and even China. Why United States will not let NASA to use the synthetic aperture radar? Because the synthetic aperture radar can see, as I say, can see the signature of submarine. How can synthetic aperture radar see submarines? And how can synthetic aperture see the bottom topography? It's all because of current and wave interaction. Submarine, the ocean surface, ocean bottom, the water is not uniform. The water density is the lightest at the surface and densest at the bottom. The water, the heaviest water, the most dense water is at 4 degrees centigrade. So if you go down to the deep part of the ocean is always 4 degrees. Because it's so heavy, it sinks to the bottom. And the top surface is changed seasonally according to the season of the year. So on the surface of the water, the temperature is near, say, like sometimes it's 20 degrees, sometimes it's 30 degrees, depends. And then this temperature keeps dropping gradually until you down to the 4 degrees. And as it drops, the top surface, because of the stir of the waves, of the wind, it's pretty uniform. So the top surface will come down and then gradually decrease. This first uniform layer is called the thermocline. And the rest of that is the natural stratification. When submarine goes through a layer, that the density is different. But when the submarine goes through that, the submarine propeller actually makes the water to be uniform. And once the water is uniform, the density becomes uniform. So this part is heavier than the ambient water, so it will sink. And the bottom part is lighter than the ambient water, so it will float. So as a result, the wake of the submarine will collapse from a circular wake to collapse into a pancake, flat. Once they collapse, so the water will rush in to fill the gap, and that create a internal wave, and the internal wave will actually create circulation pattern on the surface. And from that circulation pattern, it causes the very tiny current gradient, and that current gradient will cause the surface wave pattern to change. And surface wave pattern to change give you light and a dark contrast on the surface. So the submarine can be detected by synthetic aperture radar. And U.S. Navy depends heavily on their submarine. Of course, they want to know where the Russian submarine is, but they don't want to reveal the location of their submarine. So the DoD says, stop. So NASA stopped. And even though NASA stopped, we still can see this kind of feature in the bottom. And there are theory, wave current interaction theory. Most of this bottom topography is only visible in shallow water. The shallow water has a tidal current. And as tidal current flow over the topography, in the hump, the bottom topography may hump up. And in the peak of the bottom topography, the ocean depth is smaller. So the current is faster, and over the deeper part is flows slowly, slightly slower. So this fast and slow current change gives a current gradient, and this current gradient causes the wave feature to be different. So when you look at this, you want to, in a synthetic aperture radar, you have bottom topography, and this bottom topography, of course, is useful information. But another useful information is actually the wave condition. But if you use this to study wave, these are so non-uniform, and you really want to get rid of the bottom topography influence on the surface. So if you use the 2D HHT, you can actually separate this picture into these two pictures, and this was done by using Delaunay triangulation. Yeah, and this was I don't know how much time they use in computation, but they successfully separate the wave part and the bottom topography part totally separate, so it's feasible. And this paper will appear in the second issue of the Advances in Adaptive Data Analysis. And another obvious application for two-dimensional EMD is for medical research. Medical research, they can take an original image of a patient, yeah, and the doctor will train to look at this and tell you whether this person is okay or this person has a problem. Yeah. Now you look at this and train the person at this stage is much better than computer, because the trained person, our brain and our eye are very good to discern slight subtle change, and they also use heuristic, use reason, and they totally adapt to each individual image. So they can read a lot of things out of this image, especially the experienced person, experienced radiologist. They have no problem finding pathological phenomenon from this image. But for an untrained person, some help is really needed. So if we decompose this picture, this image, using 2D EMD, this actually is done by Nuance from France. This paper again appeared in Advancing Adaptive Data Analysis issue number 1. Yeah, if you download, you can get this. So when you decompose this picture, and if you collect mode 1, the smallest scale, then that's give you this. So you compare this picture with this picture, you see what happened is that, for example, over here, you don't see it very clear, but here you see extremely clear what happened over here. And the other thing is that this shell and this shell, with this shell, you also see another layer outside, and you see this layer, the discontinuity start to show up, and even in the uniformly grayed area, you start to show different density. Whether that is useful or not useful, I'm not sure. Okay, but this kind of picture start to call attention of some physicians, some radiologists. Yeah, the radiologist was trained to read this. They are not trained to read that. So this is something new. My daughter is a radiologist. I showed this picture to her. She said, "Well, this looks great." I don't know what you're doing here. Yeah, but I have talked to other radiologists. Other radiologists said, "Well, this is interesting." Yeah, because it actually brought up the contrast of this sometimes pretty uniform picture. Like even here, you get a different structure, and this boundary becomes clear. Yeah. Whether that is useful or not, we don't know. For example, even oncologists, these people worry about cancer. This cancer tissue are quite different from normal tissue. That they are contrast in texture, and they are also contrast in background. Because once you get the cancer, the cancer grows very fast. They need more blood, they need more nutrient, and so when you take a image, whether that image has a background change or not, that's also something that we want to find out. So this kind of picture is what we are trying to do. Here is another picture that you actually is the original image. You can do mode 1 and mode 2, mode 3. Then this is the residual. And the pictures, then you can combine this with that, and get a different kind of scales to reconstitute the pictures. This, I think it's done with the radial base function that the French people are doing. And they also use this to find out the image of the blood vessel. This blood vessels, if you zoom in, you find this this vessel, and you do a EMD, you get rid of a lot of the gray background. And once you get the gray background, and you will reconstruct the residual after you get this residual one, and then you zoom, you get this. And whether this is better than that, it's because that the background is less, and also this is more clear. Again, we have to talk to the radiologist. And I talked to the French people. They say they are working with radiologists. They think this will help. But I have not worked directly with any radiologist other than my daughter. My daughter told me that whatever I have done is not that helpful. So this is a toss-up. And what happened is that indeed, like this little, if you take any section, you will see that the original data, after you remove that, it becomes this. Whether this is better than that, from this one section you can see. But from the whole picture, you look at it, you compare this and that, or you concentrate in this little area to that, whether you can immediately say this is better than that picture, I'm not quite sure. But it indeed brought up certain feature becomes more clear. That's possibility. So the 2D EMD right now for medical application, the jury is still out. We have to ask the physicians or the radiologists to make the last call. And EMD by slice. All of the previous one is very time consuming, and it depends upon the smoothing, depends upon the solving of simultaneous equation and all that. So finally, this actually was the original proposal that I made. When I first developed HHT, the influence of Hilbert is very heavy on me, and the influence of wavelet is also heavy on me. So at that time, I asked myself, see how wavelet deal with a two-dimensional image. It turns out that the wavelet at that time has two basic approach. One approach is the so-called Mexican hat. It will get the two-dimensional pattern uniformly from one point spread out. So the wavelet pattern is a symmetric circle going out. That is more like a radial base function. The other one is slice. Slice means I'll cut the picture in different direction. And I have wave in this direction, but in this direction there's no more wave. So that's more directional. So if it's directional, then we can use two-dimensional slice to cut through the picture. So what we did is to take a picture of of the water surface. This is the water surface picture that we took at the wave tank that I had at the Wallops. Yeah, and this direction is downwind. The wind is blowing very gently. You see these little ripples, and this ripple. Actually, I think this series has a. You look at this wave surface is propagating, and the next one, the surface. You see the surface. This surface, this part is collapsing, and this collapse causes another pattern, and this pattern is more clear, and it even radiates out. Yeah. So this is the kind of image that we want to analyze. And how do we analyze? Because this one has a prominent direction in here. If we cut slice in this way, then we should be able to see all these changes. Yeah. So what we did was we cut each pixel by slice. This picture actually is 286 by 286, so it has 286 points. Yeah. We cut this, and after we cut it, then we will analyze each section and to collect all the first component. And the first component, then we put all the first component together. This is actually the final image. At that time, we immediately find a problem in this approach. The approach is that you see these streaks, horizontal streaks, there are lots of horizontal streaks. What caused that horizontal streaks is actually slightly mode mixing. Yeah, and it has jumps. From one streak has another jump. Yeah, so but even that, you can still see the deformation. This is the first one. This is the second mode. In the second mode, you see larger wave, and the streak is still there. From one slice to another slice, it has a pretty big jump. And the third one, you start to see this crossing pattern. This crossing pattern, actually, if you look very careful, you can see this already. But in this one, it specifically brought it up. And this actually looks really more like a soliton. In other words, in deep water wave, you also have surface wave act as if they were soliton. They were crossing this. You can see this each streak still clear, but when it comes across the other wave, it will almost go direct through that. And they even suggest some phase jump over here, which is the characteristic of soliton waves. So if you do this slice and reconstruct this slice by slice, if you look at each slice, this is the big wave, and these are the small wave in front of it. Yeah. For each slice, you can see this wave change very clearly. And with this slice, of course, we can decompose into different modes, and each mode we can do a Hilbert spectrum. This is the Hilbert spectrum built from each slice. Now you think, this is horizontal distance, this is wave number. So each slice, and then if I glue all the slices together, what I got? I get a solid body with density difference, and that will become the Hilbert spectrum of the picture. And this is the only way that I know of how to get a Hilbert spectrum of a picture. But this picture, however, looks very interesting, there are some higher energy, there are some different energy level. Now the Hilbert spectrum is four-dimensional. Yeah, X and Y, Z. This is a physical distance, and here actually you have density. The energy is actually the density. But this spectrum has a fatal flaw. What is the fatal flaw? It's because we imposed a requirement of positive frequency, a positive wave number. So whether the wave is propagated for time, we have no problem. The time is always propagated positive. So we always have frequency positive. But for wave, the wave can propagate this way, and wave can also propagate the other direction. So if you designate this as positive, this perfect alright to wave to have negative wave number. Once we impose this positive frequency, we actually force all the waves propagate in one direction. We don't have reverse direction, but the wave could reverse, and that directionality we have no way to recover. In other words, if I cut a surface like this, if we only look at the surface, there's no way we can tell whether the wave is propagated this way or wave is propagated that way. Yeah. So we imposed the positive wave number, and that indicates that the wave only propagates in one direction. Yeah. So I think two-dimensional EMD deserves a lot of attention for the future development, and that we have done that, and we have generalized this slice method. Yeah, we have introduced ensemble EMD into that, and actually make the jump between slices disappear. Yeah, and that's a improvement. Another improvement is that we have a different way to slice it, not only X direction but also in Y direction, and then recombine the X and Y direction to get a very good two-dimensional surface. Yeah. So that we are pushing forward on that. There are some problems need to be solved, like how to do maximum, minimum, how to resolve the edge problem, and also what is the 2D equivalent of Hilbert transform. Yeah, the 2D equivalent of transform, if you do slice, we can do it. If you do any other method, I don't know how to get the equivalent. And then another question people may ask is that, do I care about the two-dimensional Hilbert transformation to give me wave number or whatever? Yeah. Most people think, maybe I don't. Yeah. But there are problems you do. For example, if I'm doing a turbulence study, right now we do turbulence study mostly in 1D or at most 2D. If I get a 2D turbulence picture, like by tracking the particle motion, I think most fluid dynamics would like to know what is the scale distribution, what is the frequency distribution, what is the wavelength distribution. In that case, we are looking for two-dimensional equivalent of Hilbert transform. And two-dimensional Hilbert transformation is not clear-cut available. Yeah. So those are all the problems that we face in the two-directional EMD, and this is the direction that we are working on. And then if you generalize this 2D to 3D, so who cares about 3D? Yeah, you do, because if I have a material, and this material is inhomogeneous, and I want to find out the inhomogeneity of this. Then in that case, you have to use 3D. And as I said, 3D, using any other method, use radio-based function, use whatever, I totally lost the geometric intuitive picture of that. See, how can I introduce a body, which is the maximum body, which is the minimum body, and then I take the difference between maximum and minimum? I lost that physical picture. But if you stick to slice, you can cut 3D into surface. Each surface you can cut into slice. So you may be able to do that in 3D. And in fact, we tried, and that slice approach, and that actually generalized the method to 3D. One new development that's developed other than us, it's in general on the EMD. Instead of using envelopes, instead of using envelope surface and all that, there's a new approach is trying to use diffusion equation to generalize, to produce this smooth surface. See, what we did in the envelope is trying to produce a smooth surface and then take difference from the smooth surface. So this new approach is identify all the extremas and let the extrema be a higher concentration of material and let this material diffuse. And as this diffuse, it create a more general, more smooth surface. And then you take the original data, difference between your original data with the smooth surface, and get the small scale picture. So that is a total new approach. Yeah, I have seen that people use that in 1D, and I also seen that using 2D. Yeah, and the people that using 2D has shown this result to me. And being diffusing, then you know that the surface will gradually spread out, and as a result, the decomposition that I have seen, none of that actually carry the fidelity of the original image because everything's smeared out rather than actually follow the data. So I think that approach may work. Then you have to control the diffusion because most of the diffusion equation is linear. Yeah. So all the spreading are actually linear. So those are the development of the two-directional EMD. And if you people are interested, I can advertise that in this new journal, next year, there will be a special issue on two-dimensional EMD and its application. Why I know that is because once the new methods get patented, we're going to print that in the issue, and then we invite other people to present their view, and then we have a big comparison of different methods on certain image and see which one comes out better. Yeah. So that's the end of the two-dimensional okay. This is my thoughts at the end of 2008, and very befitting. This is the last day of 2008. I'll give you sort of a summary of what my thinking, my current thinking. The method was developed in 1995. I perhaps told you that this has come out all of everything started from a mistake I made in analyzing the wave data. And I used Hilbert transformation. I did not take out the mean, take out the reference, and I struggled to put that back together in 2 months. Okay, and eventually the paper was published 1998, 10 years ago. So the paper appeared 10 years ago, and the method appeared more than 10 years ago. And the method now is getting more attention. Now, so having working on this field for 10 years, and I have lots of time to sit there to think about the method. I remember reading Sir Isaac Newton. Sir Isaac Newton says the following thing: I frame no hypothesis. He said that in all his work, there's no assumptions. Yeah, he said that for whatever is not deduced from the phenomenon is to be called a hypothesis. And a hypothesis, whether metaphysical or physical, whether of ocular or quality of mechanical, have no place in empirical philosophy. At Newton's time, the word science is not there. So everybody are studying philosophy. Yeah. So Newton is a philosopher. He's a natural philosopher. Yeah. So everybody study philosophy. It's an experimental philosophy. Yeah. If you use this word today, I think the editor will throw a paper out. What do you mean experimental philosophy? It's experimental science. Okay. So that is what Newton said, that we should not make a whole lot of assumption. A truth is ever to be found in the simplicity, and not in the multiplicity and the confusion of things. You think all these great scientists has a common thread of thoughts. So Newton is emphasize simplicity. Yeah, Newton does not like hypothesis, and this the emphasis in simplicity is carried on by Albert Einstein. I remember quote Einstein before. So everything should be made simple, but not simpler. Yeah, and that's very profound. Everything should be made simple, not simpler. Simpler means make simplification. For example, what is simple? F equal to ma is simple. What is simpler? Then you say, assuming the water is frictionless, assuming the water is incompressible, assuming this, assuming that. That makes it simpler. Yeah. The simple is a physical rule, physical law. Mathematicians are looking for proofs. Scientists are looking for law. Proof is absolute. Law is relative. Newton's law need modifications. Yeah. But the Euclidean proof, nobody can tamper. So that's the difference between the mathematician and the physics and the scientist. And what the engineer do? Engineer do is to create or implement whatever is possible. Okay, you build something based on the given law. So this is what Newton said. Newton says everything should be made simple. And Newton indeed had a lot of contribution. And his major contribution, of course, is Newton's three laws in motion, F equal to ma. But the other really more important thing, I think, is his invention of calculus. But Newton should not claim the sole credit for invention of calculus, because this gentleman, Leibniz, has an equal right to make this claim. Newton summarized his thought on calculus in 1665, around 1665. Leibniz published, but Newton never published anything. See, Newton is a very secretive person. He will find calculus, but he will not publish it because he cannot recognize he cannot make the whole argument so tight. And so when he first published, eventually he published his calculus, instead of the Leibniz notation of dx dt, x plus dx as increment, Newton's original notation is x plus 0. And he said, but this 0 is not 0, but it's a small. So you use a notion of 0, and when that small quantity multiplied by anything, it becomes 0. So people get totally confused. Okay. So is Leibniz. Leibniz used this dx or dt, think it is small. When they try to publish, Newton and Leibniz approached the calculus for very short of later stand of rigor. Yeah. We now see their proof has been in truth mostly heuristic, hodgepodge, and mainly ungrounded geometric intuition. A lot of methods start like this. When it first started, people think, well, gee, this is not right. Especially the big things like calculus, it's so new. Then people has resistance. And part of the resistance is the mathematical tool hasn't catch up with their invention. Yeah. So Leibniz used dx dt. Newton used x dot. Yeah. They are equal. Now because of the Leibniz used integral, Newton used whatever. Newton did not really work heavily on integral calculus. Yeah. Newton thinks integral calculus is the inverse of differentiation, but Newton didn't call the differentiation. Newton called it flushing. Yeah. All this modern notation are all Leibniz notation. So Leibniz published his paper in 1675. A year late, 10 years later than Newton claimed that he first summarized all his work in calculus. And Newton accused Leibniz for copying his work. And eventually Leibniz fell in a trap by asking Newton to investigate. Actually not ask Newton, ask the Royal Society. Because at that time, the only learned society is Royal Society of London. So Leibniz said, well, if you think that I copy you, here's all my notes. Yeah, you can organize a committee to investigate. So Newton did that. Newton was the president of the society. He appointed his friend, and legend has it that the committee never met. But Newton wrote the final report and accused Leibniz as a plagiarist. Because of that, the mathematical community in the continental Europe and the England totally split, and they split so bad that the British refused to use this notation for calculus, and they keep on putting dots. Yeah. And after a few dots, it's become so confused that they never really progress very fast. Meanwhile, the continental people use this very nice rational symbol that we still use now, and made lots of progress. And Newton is so dominating in England. Everyone wants to study mechanics. Of course you follow Newton. Everyone wants to study mathematics, you still follow Newton. So in England, even the mathematics does not progress very smoothly, very far, because in England, mathematics is mechanics. Yeah, you study fluid mechanics, you're a mathematician. Example, Stokes. Stokes is Newton's chair, Lucasian chair at Cambridge. He proposed the Stokes law and all that. He's a mathematician. Yeah, But what he studied fluid mechanics. Yeah. And that bond tied to Newton was eventually broke up in the 19th century. This operation at the beginning was ridiculed by many people. See, George Berkeley, in a paper called the calculus, he said that pointing out that natural science grounded in the calculus requires just as big a leap of faith as theology's ground in the Christian revelation. This is, if you believe in whatever the mechanics based on calculus, might as well believe in the second coming of Jesus. Yeah. So the hostility is very, very strong from the mathematical side. But eventually, however, the rigorous calculus was established by Cauchy, Riemann, and Weierstrass. And what they did is because they introduced a limit, the concept of limit. Yeah. Without the concept of limit, the calculus is very difficult to establish. Yeah. But once they established the limit concept, the operation, the calculation is still the same as Newton used and as Leibniz used. So they did not change the calculation, they did not change the operation. However, the objection from the mathematical community forced Newton and Leibniz to call them their method, calculus, not as part of mathematics, but as an algorithm, a method for calculation. So it's the same with our old friend Fourier. Fourier's method is rejected because lack of rigor. But everybody used it. And eventually there was the convergence and the convergence of Fourier transformation was proved by in 1935. How they prove it? Only after they invented the measure theory. They invented the Lebesgue integral. They say that if you have infinite many jumps, it's fine. Yeah. And as long as the jump is denumerable, is countable. If you can count 1, 2, 3, 4, 5, you can count infinite many jumps. As long as it's countable, you can arrange them into sequential number. What is countable? All the natural numbers are countable. 1, 2, 3, 4, 5. You can count to infinity. It's countable. Yeah. What is not countable? Not countable is even all the rational number is countable. Because all the rational number you can arrange 1 over 2, 1 over 3, 1 over 4. You can all arrange that. So all the decimals are countable. What is not countable is irrational number. Yeah. So for Fourier's integral, you can have all the countable points you have jump. In other words, you have every rational number you can have jump. Then they can draw two lines to isolate this jump point. And then mathematician, if you use intuition, say, oh, there are so many, infinite many jumps, then they cannot converge. But mathematician eventually prove, if you have countable number of jumps, then I can exclude the jump, and I can prove this jump place, the total measure of the jump is 0. So the rest of that is still converges. Okay, so through that they establish rigorously the Fourier transformation. But after they established the Fourier transformation, did they change the operation? No. The Fourier transformation is still the old Fourier transformation, except that the mathematician prove it to make sure that it converge mathematically. How many people use Fourier transformation know about the proof of punctual? I think I can guess. I think less than 1 in 10,000 or 1 in 1,000 at least. Not many people care about that. The people use it. Okay, so people's attitude perhaps is more like this guy. I have introduced this guy to you. Have you ever seen this person? No. This person is Heaviside. Heaviside is the electric engineer. Yeah, he was eventually elected to the Royal Society as a member of Royal Society. His claim of fame is to define delta function and step functions. Yeah, perhaps I did not introduce him. Heaviside. The step function, the delta function. The delta function is that this function is zero everywhere except at one point. And what is the property? Is the integral of this one point is 1. Okay, the integral from minus infinity to infinity to the delta function is 1. And the delta function has no value anywhere except at that one point. Okay, so when he first introduced this function, and then he said, well, not only this function, the integral of this function is step function, because it's 0 all the place. After integrate it becomes 1. It's a unit step. The rest of this from 0 to 1 is a step function. Mathematician gets so mad at him. He said, look, this cannot be defined. Mathematician says, I can come up infinite number of functions that satisfy this property. So your delta function is ill-defined. Okay, we in the last class I give them 3 or 4 different versions of delta function. Yeah. So he got so ridiculed by the mathematicians. He eventually suffered a nervous breakdown and eventually died of mental condition. Yeah, he retired very early at end of his career. But he said something which is, I think, is memorable. As he said, why should I refuse a good dinner simply because I do not understand the digestive process involved? Okay, when we eat a very good meal and our body absorb it. Yeah, I don't understand this, how this process I digest the food. But do I enjoy? Should I therefore not enjoy my dinner? No, I still enjoy my dinner. Yeah, so certain method I may not know the final proof. Yeah, but it's useful. Heaviside's method, delta function, step function, was ridiculed by mathematicians. But eventually, one very wide use, especially in the engineering community, like double E and all that. In fact, if you use delta function, use step function, you simplify a lot of this transformation, like Hilbert transformation, whatever, becomes so simple. Yeah. So people say, well, it's fine, we'll just use it. And now it's being accepted. Why they accept it? The mathematician take another step. Not because that he took delta function back. As a mathematician take a step forward, they call it the functional analysis. Instead of a function, it's called a functional. That means a group of functions all had the same property. So you have to liberate your mind to think different, think outside the box. Yeah. When you think like a mathematician, you usually think that you have to have the rigorous proof. Yeah, rigorous proof need a new concept. And Olivier Heaviside brought out this function, his delta function, and eventually lead to the functional analysis. This is my advice to you. When I teach in the United States, I always show this as the first view graph with this. 学而不思则罔，思而不学则殆. This is Confucius saying. What do you mean? It means if you want to learn something, you have to think. Yeah. If you only think and not learn, then you will never really, you will be exhausted. Yeah. If you learn without thinking, you will never learn. If you think without learning, you will be so tired, and you actually put yourself in risk. So learning is actually two steps. You think and you learn, and then you think more and learn more. Okay, this is the way. So to think, everybody should think, and I advise you to think outside the box. Yeah, there was one paper I read. I can share that with you. This paper was published maybe 5 or 6 years ago in Science. A very short paper by a physician. The physician's name is Paydafar, Paydafar, P-A-Y-D-A-R-F-A-R, Paydafar. He's a physician in Massachusetts. He once published this paper. It's called the Algorithm for Creativity. So creative. Can you be creative? Is there a way to be creative? So he summarized the 5 rules, and the 5 rules was published in Science. The 5 rules, as I remember, number 1 is to read extensively. Not just pick up one field and read only that one field. Read extensively means read all kinds of books. Yeah. If you read only one field, it may not help you, because you may think that, gee, every possible solution or very possible thought has been already exposed. It's not so. So you have to read extensively, see what's going on in the whole world widely. Second is think outside the box and think at leisure. Don't be rushed to say that, okay, I only have this rule, I have to follow this rule, I cannot think beyond this. You think in Chinese, should I say, sorry, I use one Chinese, okay, 想入非非. You have to think outside the box. You have to think the unthinkable. That's what I say, 想入非非. Fei means negative. Yeah. So if you think outside the box, you will get some new ideas. The third one is that don't stop improving. If you get some idea, you get some method, don't be considered, okay, I stop. That's it. You try to see whether you can improve this. And many of the new methods actually come from the improving the details. The fourth is that you insist on looking the original data. Don't let people process the data and give it to you. So say, here's the data. I have already taken all the noise away, and this is so clean. And you don't know what they take it away. They may throw away a lot of valuable information already. Okay, you want to see something in its original form. Yeah, you don't want other people to do that dirty work for you. The final thing is to make friends with smart people. The smart people has a different way of look at things. Then if you have a lot of smart friends, sometimes they may not try to solve your homework problems, but they can give you ideas of what other things you can do. Yeah. So those are the things. And then when you learn, you have to think. You have to think. And when you think, don't think that you can solve all the problems. When you think, you have to learn from other people. So these are 2 steps. Yeah. Now, where does HHT stand? HHT stands as a crossroad. I will cite this as one of the conclusion of the class. This was composed December 17th, 2008 in Guangzhou. It's just a couple of weeks ago, to be sung to the tune of International. I don't know how to sing that. Perhaps Tom, you know. International? International, of course. You know that, huh? This was composed by Ingrid Dobishi. Ingrid Dobishi is a professor at Princeton University Math Department, and she is the inventor, I would say the mother of wavelet. Okay, I've tried to get her to help me study HHT for 10 years, and finally she turned around. She said, "Yeah, I will do that." And actually, she was at the second international conference on the advances of Hilbert-Huang transform and its application. Yeah. Some of you were there. Song Zhong was there, and Huang Adam was there. At that meeting, Ingrid composed this song and asked everybody to stand up and sing this verse to the music of International. And the verse says that you can use wavelet or Fourier and find something that is useful. But if you want something new to say, you cannot be any old fool. Actually, this song was composed to me, and she dedicated this to me. And you then find a new kind of algorithm and let it loose on the world. But before they even know what hit them, they were up their neck on work. Yeah. So she found that HHT is a new algorithm. Yeah. And now they will try to find out why it works. Rushing into to meet, this is a typo, MEET. Rush in to meet your frustrating challenge. They filter, they stretch, and squeeze. I have gone to every possible math department. If they ask me to give a talk, I will go there. Yeah, I will just try to show them what works. Yeah, I don't have a proof. I told them I don't have a proof. I challenge them to prove it. Yeah, so they rush in. Lots of mathematicians rush in. They try to use filter. They try to stretch their coordinate. They try to squeeze their coordinate. They do all kinds of things, but always some signal through a monkey wrench and make them huff and sneeze. So after they introduce filters and all that, they come back to and say, "Hey, I use filter." In fact, at this conference, some famous guy says, "I'll have a filter." On the spot, I pointed out to them that doesn't work. Yeah, but that did not prevent the mathematician from introducing these filters and the ideas. And look at all the data. A lot of data immediately defeat their filter approach. So your name is, of course, Northern Huang. Long may you live and smile. We're here to learn, get the hang, and we're not quit for a very long while. He said that, okay, we're going to be here. We're going to try to solve the problem, but we may be here for a long while. I think they will be here for a long while. So far, I haven't seen any light at the end of the tunnel yet. Okay, so the last one is Hilbert-Huang transformation. You will triumph. I don't know whether we'll triumph or not. I don't think it'll be very close. I can share with you a slight colored joke told by C.K. Peng. At my table, I think maybe you haven't heard the joke. HHT right now always produce result, always produce approximate result, but nobody can prove it exact. Okay, so CK, a director of nonlinear physiological laboratory at Harvard Medical School, told a joke in my table when we have dinner. He said that there is a mathematician and a physicist. Yeah, they were doing research at the university. They are both frustrated. The problem they cannot solve, so they come out to their room, stand in the hallway, and they were slightly depressed. And then presently the God appeared. Yeah, so I will cheer you guys up. How? She said, at the end of the hallway, see there? The prettiest girls still there. You can go there. Whoever get there first can kiss the girl and make you happy. So, but there's one rule. You go there, you cannot just run over there. You have to walk over there. When you reach halfway, you have to stand there, count 3. And then you walk the rest of the place. And then you walk half, you have to stand. Every time you reach half of the rest, you have to stand there and count 3. Okay, so the physicists immediately start. They walk and count 3, walk and count 3, and kiss the girl and come back. And find the mathematician still brooding and get so mad. He says, God is unfair. He says, why? He says, give me a problem that is impossible to solve. The reason is that if we add 1/2 to 1/4 to 1/8, you have to add forever to get to 1. So the mathematician said, there are infinite many, this is infinite series. The infinite series multiplied by 3, that's forever. You'll never get there. But the physicist, I get close enough. Yeah, I get there close enough and I got the keys and now I'm back. Yeah, the mathematician still worry about the last 1 over, say, 2 to the nth power. Anyway, so HHT is one of those things. It gets you close enough to your goal. It may not be exact, but it's very useful. Should we stop? No. We should continuously to improve. For example, when I first introduced EMD, there are lots of flaws. Mode mixing and effects and all that. But after Zhaohua Wu come to work with me, and we come up with the ensemble solved many of those problems, made the EMD much more serviceable. Yeah, EEMD the final answer? No. EEMD produced something which may not be IMF. Yeah. So all of this problem will continuously working. Whether we can actually make it to the final form or not, I don't know. Yeah. So, but EMD is easy. It's very simple. Yeah. This is my grandson. And when this book came out, I give it to him, and he opened it up and started to read. But you find that there's some helping hand. Somebody's holding the book to him. So even she can read it. Even he can read it. And how much he understands, I don't know. My conclusion is this. It's better lucky than smart. Yeah. In doing research, I perhaps should not say that, but this is true. A lot of time you really have to be smart, to be lucky. Give you an example. Carl Wilson is a Millikan student. Millikan get Nobel Prize and becomes the president of Caltech for 30 years until he died. Yeah. He will not call him as president. He called him the chairman of the executive committee. The executive committee is 3 persons, and he's the chairman, make all the decisions, of course. He's the president. His student is Carl Wilson. And Millikan got his Nobel Prize by measuring the charge of electron. And this is the mist oil chamber. It has a very fine mist, and then each one attracts the most elementary charge, and then they move in the magnetic field to form a track, and then you can deduce the charge. And he found the minimum, the smallest charge is 1 electron. He found the 1 electron charge is how much, and he determined that. So all the charge, all the particle going into one way because electron charge is negative. And the student was sitting there and look at the chamber, and one day 1 electron goes the other way. And that's pure luck. It's 1 in a million or whatever. Sometimes it happens, you never catch it. Then he immediately said, aha, I found a positive charge. Electron is negative charge. And people are thinking that by symmetry there should be a positive charge, but nobody has ever seen it. He found it. He's very lucky to find it, and he got his Nobel Prize too. So it's better lucky than smart in research and in many other things. And here, I will say this. I'm lucky to have found this simple method. And I think you are smart to take this course. This method is really, really simple. Yeah, you look at it, perhaps you think that I could have found this. Many of my friends says I could have found it. I say, of course you could have found it. But I'm lucky to have found it. But take the smart people to appreciate. So I just wish everybody of you continue to have good luck. Thank you very much. Yeah, this is the end of the class. Any questions? No more questions? As I said, I thank you very much to take my course, and I hope you have learned something. And if you have any questions, we can keep touch from now. Next semester, I'm trying to offer a class with the special topics. And the special topics, I'm thinking of teaching jointly with one of my colleagues, and that class will discuss all the algorithms that we use. And the goal of the class will be, after the class, we'll have a menu of HHT for everybody to use. And in the class, the homework will be try all the possible algorithms and find all the mistakes and rules and improve the algorithm as it is. Okay? All right. That's the advertisement. And the class is over unless you have any questions. Sure. 没有，他们 the question is in BEMD, the two-dimensional, how you solve the saddle problem. Many people treat in a two opposite way. One class is ignored, other class is counted as both maximum and minimum. Okay, but if you start to use slice, then you don't have that problem. You slice one way is always minimum, slice other way is always maximum. Yeah. Yeah. 斜着看也是最大值啊。Yeah, 有的时候是 inflection point. Yeah. 但是 even if you have inflection point, through decomposition, inflection point can become extrema. Remember we in the examples that we give at the beginning, yeah. So it still may come out. Yeah. It is a wave, in other words, it's hidden. Yeah. Okay. So that's the end. If you want to participate in making the algorithm perfect, come back for the next semester. Otherwise, see you guys. Good luck. Okay. Thank you very much. Yeah. Bye bye.